Hello, and today we're going to prove that square root of 2 plus the square root of 3 is an irrational number. So some of you may have seen the proof that the square root of 2 is irrational. And this question with the square root of 2 plus the square root of 3 is a slightly harder version of proving the square root of 2 is irrational. So let's have a look. To prove square root of 2 plus square root of 3 is irrational, we will use proof by contradiction. And proof by contradiction will assume, instead of square root of 2 plus square root of 3 being irrational, we'll assume it is actually rational. And if it's rational, we can write it as a fraction p over q, where p and q are integers and q is not equal to 0. Okay. Now, what we can try to do is over here we have two different square roots. But what we could try to do is to reduce the number of square roots from 2 down to 1. And what I'll do to reduce the number of square roots is to square both sides of the equation. If I square both sides of the equation, I'll have this. And the left-hand side expands to 2 times square root 2 to square root 3 plus square root 3 squared is equal to p squared over q squared. And now the left-hand side can be written as 2 plus 2 square root 6 plus 3 is equal to p squared over q squared. And we now have square root of 2 square root 6, we can rearrange as p squared over q squared and minus 5. So 2 plus 3 here is 5. Okay. Now we can write the right-hand side fraction as a fraction with a common denominator. And now we divide both sides by 2. Okay. Now we have the square root of 6 is equal to p squared minus 5q squared divided by 2q squared. And remember, since p and q are integers, it means p squared minus 5q squared and 2q squared are also integers. And also, since q was not equal to 0, the denominator of the fraction is not equal to 0, which is 2q squared. So it turns out that square root of 6 is rational and can be written as this fraction on the right. So if we make m equal to p squared minus 5q squared and n equals 2q squared, we have square root of 6 is equal to m over n. And if we square both sides, we have 6 is equal to m squared divided by n squared. Now we can rewrite it as m squared equals 6n squared, or 2 times 3 times n squared. Okay, so now we can have a look at the exponent of 2 in the prime factorization of the left-hand side and the right-hand side. So the exponent of 2 in prime factorization of m squared must be even. And this is because if we take the prime factorization of m and square it, each of the exponents will multiply by 2. So the exponent of 2 will be even. And the same thing happens to n squared. So exponent of 2 in the prime factorization of n squared is also even. However, we are also multiplying by 2 here. So we have an even exponent of 2 in the prime factorization of n squared, but we're also multiplying by another value, another 2. And since this 3 over here has no factors of 2, it can be ignored. So it turns out 6n squared exponent of 2 in the prime factorization will be odd. And this is a problem because the exponent of 2 in the left-hand side is even, but on the right-hand side is odd. And it means this equation is impossible. You can't have any values of m and n integers that satisfy this equation. And also note, you can't have n equals 0 either. So n is not equal to 0 because 2q squared is not equal to 0. And since n is not equal to 0, m can't be equal to 0 because if m was 0, then the right-hand side of this fraction would be 0. However, the square root of 6 is not equal to 0. Okay. So it turns out we have a contradiction here because we can't have something being odd and even at the same time. So it follows that original assumption of square root of 2 plus square root of 3 being rational was false, because all the logical steps we derived eventually came to a final contradiction over here. So that means since our original assumption was false, using proof by contradiction, we've successfully proven that square root of 2 plus square root of 3 is irrational. Okay, so that's all for this proof. Hope you enjoyed the video. Thanks for watching, and I'll see you in the next video.